So today we're going to be talking about interactive video number 4, which corresponds to your lesson task number 4 due on Monday. That is going to be about harmonic motion. And if you haven't noticed, all of these lesson tasks are created for either two types of category. Either they're very difficult for students or they're very important, or both actually. They could be a combination of both. But that's why I choose these as lesson tasks, because I think they're important. So, harmonic motion in particular. We got to think about two things when we're talking about real world application and we're trying to model it with the harmonic motion function sine or cosine. The first thing we got to think about, is it a simple harmonic motion or is it a damp harmonic motion? Are we going to just have a constant amplitude, or are we going to have an amplitude that changes? Is our amplitude a function rather than a constant function? So, looking at this problem, if you read it out, we have this, I guess, city or bay that has the highest tides in the world. It says that we're going to look at it at a 12-hour interval, and the water starts at sea level. It rises eventually to 21 feet above sea level, and then it drops to 21 feet above or below sea level, and then it returns back to sea level. The question or the statement also tells us that the tides are a simple harmonic motion, so that's nice. Gives us an idea. It says find the equation that describes the heights. I don't like that wording. I think they should have used find the function, but that's me being picky. So let's think about how to describe this. First, we're going to do a rough sketch of it. I'm going to do an XY plane. It's actually better if I don't draw it, if I use technology to draw this out. If I use technology to draw this out, boom, and I'm going to make the x-axis very big because I always mess that up. Well, I make my x-axis, my y-axis, all that good stuff. I know it starts at sea level. Let's let the x-axis represent our sea level. So that means that at the starting position, my value should be right here. My point on that function should be over here. It eventually rises to 21 feet above sea level. So somewhere it rises all the way to 21 feet. And then it's going to go below 21 feet, somewhere around here. And then it's going to go back to sea level. So if I connect the dots, something like that. Now, how do we know if we're going to use sine or cosine besides it looks like it after we've drawn it out? Well, the idea between determining if you're going to use a sine function or a cosine to model your real-world application problem is determining if your problem starts off at the very max or it starts somewhere in the middle. In our problem, we start at sea level and then rise up. So I shouldn't choose the cosine function because cosine of 0 radians is equal to 1, which means it hits its maximum. Instead, I'm going to use the sine function, which is going to be in the form of f of t is equal to a times sine of omega t. All right? We're not going to talk about vertical shifts. We're not going to talk about horizontal shift. If you want to think about that for those problems, well, then I guess your c moved upwards. Like your entire c just moved up, or your entire c just moved down. That's not going to be with us for at the moment. We're just thinking about amplitude, and we're thinking about this omega. So, we know it's 21 feet right here. Now, we need to solve for all of them. Well, we can solve for amplitude right now, actually. Given our graph sketch, our amplitude is from here to here. The distance from the middle to the very top. Well, that's kind of clear now. Your amplitude, the absolute value of the amplitude is equal to 21. Boom. Great. We got that. Now I just need to figure out what omega is. Well, remember, omega affects, it's like a horizontal compression. It affects your period amount. If it affects your period amount, remember your period of sine is 2 pi. So any transformation on sine is going to be calculated as your period is equal to 2 pi divided by your horizontal compression, or whatever you want to call that, by omega, horizontal compression, horizontal stretch, depending. So we can calculate the period though. We can calculate that. When does the function repeat? Well, if I start from the very beginning, it repeats from here to all the way here. This is one full cycle. One full cycle. And then it supposedly repeats if it follows this harmonic motion. Well, that means this distance is 12 at a 12-hour given interval. So that means my period is equal to, I'm sorry. I can replace period to be equal to 12 is equal to 2 pi. Oops, I'm sorry. What am I doing? Yeah, I'm doing good. 2 pi over omega. If you want to solve for omega, multiply both sides omega, then divide both sides by 12. And you should get omega is equal to pi over 6. You can check the math on that. So that means my function can be modeled with my graph can be modeled with the function f of t is equal to 21 sine of pi over 6t. So that wasn't too bad. We were able to model a simple harmonic motion. Now, what if instead I gave you a harmonic motion that has been damped? What does damp mean again? That means I have kind of smacked down those amplitude. It kind of varies. It lowers. It started out high and it gets less and less and less. And we model that with an exponential equation. So let's look at this function over here, or this question. I have a guitar string. And let's just draw it out, a guitar real quick. If I draw a guitar, boom, boom, boom. I think it's something like that. I don't know. Then I have strings. 1, 2, 3. The guitar string. I'm going to pull one of these strings 3 centimeters above its resting position. So if I think about it, my string that I'm going to pull, let's say I pull this string right here. If I pull it, it's going to be something like this. I'm going to pull it up. And then when I release it, it's going to get smaller and smaller and smaller and smaller and smaller. And that means it's being damped. The question tells me it's going to be damped. But you should already have the idea that this is a damped harmonic motion, just because it gets smaller and smaller and smaller. It doesn't go back to that original height. So in this idea, we can actually calculate when I pulled it up all the way to the resting position. This is the same as being the amplitude, which is exactly 3 centimeters. Because I pulled it up 3 centimeters, and that distance from its resting position is 3 centimeters, so it's the amplitude. Well, it also tells us that we have a frequency of 165 cycles per second. And then after 2 seconds, it is observed that the amplitude of the vibration at point P is 0.6 centimeters. So let me just write some stuff down. I know when I damp my harmonic motion, I'm using an exponential decay function. And if you remember, the exponential decay function is k, that's your initial value at time 0, times e to the negative ct. This will ensure that it goes downwards. You guys work with half-life, which you guys use base 2 instead of base e. Well, I can use base e no matter what, because no matter how much I am decaying, if I'm decaying by half every single time or decaying by 20% or 30%, I can model it all or rewrite it in terms of base e. You're able to do that. That's in pre-cal algebra. So this is going to represent that exponential decay. And we're going to use it to damp our system or to bound our system above and below. So it's going to be multiplying cosine. And why did I choose cosine? Because when I picked it up, that's my initial starting point. That's the maximum height it'll reach. So cosine of, omega t. We need to figure out what our function is, because there are a lot of unknowns. The only unknowns that I can actually have is t. Everything else has to be a fixed value. So I need to solve for k, I need to solve for omega, and I need to solve for c. Well, some of them I've already know how to solve. Well, let's just think about this real quick. When I pulled it up 3 centimeters, that's the initial starting amount. So that means that f of 0 is equal to k e negative c times 0 times cosine of omega times 0. If I plug this all in, I get f of 0 is equal to, what is that? F of 0 is remember, our output is our initial displacement. I pulled it up 3 centimeters. So f of 0 is actually equal to 3. Is equal to k, and this is 0. Cosine of 0 radians is equal to 1. So I'm just going to multiply that by 1. 0 radians to the right of the unit circle, that's 1 distance for the x-axis, or x values. And now everything raised to the 0 power, this is 0 of course, everything raised to the 0 power is 1. So this is k times 1 times 1, which means that 3 is equal to k. Now, if you look at your definition, they tell you that the initial amplitude is 3, but this is just the work that goes in the background. This is how we can figure it out. So we get 3 to be our initial amplitude. Great. That means I have f of t is equal to 3e to the negative ct times cosine of omega t. Well, now we need to figure out for omega. How can I figure that out? Omega itself. Well, if you notice, they gave us frequency. Frequency is related to period, and period is related to our horizontal compressions. So, if we remember, frequency is the reciprocal of our period. Period is equal to 2 pi over omega. So that means I'm going to have omega, frequency equal to omega divided by 2 pi, which is 165 cycles per second, over omega over 2 pi. If you solve for omega, you get omega is equal to 330 pi. We're doing great. We got more variables solved out. We're almost there. So now I have f of t is equal to 3e negative ct. And we keep t right now. That's always interchangeable to be a variable, not depending on the situation. Times cosine of 330 pi t. Great. We have that. That helps out us a lot. We know f of 0 is equal to 3, and that gave us that k value. Now, going back to the original problem, we have to use other information. Well, they're telling us after 2 seconds, so f of 2, the displacement or the amplitude of the vibration, remember the amplitude represents displacement in this case, that's where it's going to be from the resting position, is 0.6 centimeters. So that means I have f of 2, which is equal to 3e to the negative c times 2 times cosine of 330 pi times 2. T is 2, remember that. But then the displacement at 2 seconds is 0.6, which is equal to 3e to the negative 2c times cosine of 660 pi. Ooh, that's a lot. But it's actually not too bad. 660 pi. What value is that? What's the cosine value of that? What's the x value? Well, let's think about it. This is a very big number, but it's actually very simple. Cosine of 0 radians is 1. Cosine of 2 pi is 1, because that's a full circle. Cosine of 4 pi, that's 2 whole circles, is still 1. Every single time I go around a full circle, the cosine value is 1 in that case, because it starts at 0. Notice that 660 pi is divisible by 2 pi. That means I'm just going into a full circle 330 times. It should still be 1 in our case. So this is equal to 1. That's nice. That's very nice. Sometimes it's not like that, though, so you got to be careful. But I have 0.6 is equal to 3e to the negative 2c. Now, this is an exponential equation. Go back to pre-cal algebra, recall how to solve an exponential equation. You need to isolate the exponential function. So let's isolate that guy. I got to get rid of that 3. To get rid of that 3, what operation is a 3 doing to that function? It's multiplying. So I got to divide both sides by 3. I get 0.2 is equal to e to the negative 2c. Well, my exponential function is now isolated. I'm happy. Great. But how do I get rid of an exponential function? Because my variable that I need to solve is my exponent. How do I do that? Well, it's the idea of, how we solve for, let's say, sine of whatever, right? If I'm struggling in solving for it, I apply the inverse function to it. Because sine of x, if I throw an inverse function in that, it'll cancel out the sine completely. As long as you're in your domain and range, you are satisfied. So I'm going to apply the inverse of exponential function. And in pre-cal algebra, it's a log branch. It's a branch of a log function. That specific branch we're choosing is base e. Because I have base e, I'm using the log branch of base e. Well, that's going to be your natural log in that case. So I'm applying natural log to both sides. I'm using this function. I'm throwing everything inside this function. By throwing everything inside this function, your function and e, the exponential function, will cancel out. They're inverses of each other. Boom. They cancel out completely. We're just left with whatever the exponent is. So now I have negative 2c is equal to ln of 0.2 over, I think I'm going ahead. We have that. Then I have c is equal to negative ln of 0.2 over 2. I'll put negative. You can put negative anywhere you want, really. I don't really care. All right, so you have that. Great. Now remember, C has to be strictly positive. Is this a positive number? You have to check it. ln of 0.2 is a negative number in that case. So we have a negative divided by negative 2, which is going to be positive. So it does check out that C is positive. That's nice. So I have this. Boom. We're happy. Now I got to plug into my original function because I need to write it in terms of t. So it's not actually that bad. I have all my variables solved out, and I can just leave t as a variable now. So we can model our guitar problem as f of t is equal to, what did I have? What's k? 3e to the negative of this guy times t. Well, a negative times a negative is a positive. So I can just write ln of 0.2 over 2 times t. And yes, I get that, this guy is negative. Divided by a negative is a positive. But I'm saying I'm using this negative to cancel out with the original negative c that happened in the problem. In the original problem, we do have negative no matter what. So that negative of the negative makes positive. So this guy is actually a negative value, though. Remember that. It's actually a negative value. It looks like it's positive, but it's actually negative. So it is going to exponentially decay. So I have that all times cosine of 330 pi times t. I'm going to write that in better color. I don't like the red. That looks funny, doesn't it? Yeah, it does. I don't know what I'm doing anymore. Cosine of 330 pi times t. And I like to use parentheses to show you what I'm throwing inside my cosine function because that's confusing. So that's the idea how we can find the, harmonic motion equation, simple harmonic and damp harmonic motion, so we can model these real world application problems. They're not a perfect amount. They're not a perfect model, but they are a good model because not only are they periodic, but we can vary its amplitude and whatnot to change it up. We can change it so we can actually fix it up. Like in this case, we're damping it so we can actually make the guitar string vibrate less and less. Now, you might argue that the guitar string stops eventually. Does this function ever stop eventually? If you look at your function, it doesn't look like it, but it can. It can. It approaches 0, but it can't stop fully. It can't stop fully. So something to think about. And I'll leave it at that. I will catch you guys next time. Good luck on Monday. Take care. Bye.